So, Adam, can you hear me? Suhail, Ethan.
Yes, sir.
So let's start with this one, and let me open the data booklet as well. Just 1 second. So let's start with this case ability question, and we've got what does it say? The first thing is he's stating about he's talking about the iron atom, the electronic configuration of an iron atom, and 26 electrons. So that's iron is 26. So 26 electrons is going to be 2p6, 3s2. Then there's going to be 3p6, and then there's going to be 4s2, and then you'll have your 3d, which is going to be 6 as well. So I think that's 26. So then you've got iron 3 plus iron. So you're going to remove 2 electrons from 4s and 1 from here. So it's going to be 3s2, 3p6, and there would be 3d, 3d5. Then it says calculate the pH of 0.25 mole per dm cube FeCl3 solution. So remember all acids, they dissociate, ionize, and they produce an ion and an H plus 1 ion. I mean, they produce something which is A and an H plus 1 ion. So Ka is products over reactants. So these two have exactly the same concentration. In this case, this is your A minus 1, this is your H plus 1. So these two are going to have the exact same concentration. So Ka is going to be product concentration, which is going to be H plus 1 squared. And you're going to divide that by the reactant concentration, which is going to be your acid. So now in this case, he's already given you the concentration of FeCl3. Remember now over here you have Fe3 plus H2O with 6 water molecules. So that is basically FeCl3, because when you dissolve FeCl3, the same amount of Fe3 plus ions are going to be produced, and the same amount of complex ions would be formed. When FeCl3 dissolves, this is what's going to happen, that FeCl3 dissolves. It's going to dissociate because it's soluble. It's going to form Fe3 plus aqueous and 3Cl minus 1 aqueous ions. The Fe3 plus aqueous is going to mix with water molecules, and it's going to form a complex, which is going to be that Fe3 plus would be surrounded by 6 water molecules. The lone pairs of those 6 water molecules are going to be attracted very strongly to that Fe3 plus, and what you're going to get is you're going to get a complex ion, which is going to be Fe with 6 water molecules. So the reason H plus 1 is squared is that H plus 1 concentration and A minus 1 concentration, they're going to be exactly the same. Like this concentration and this concentration would be exactly the same. So instead of writing this in the numerator, what you can write is H plus 1 squared. So the thing is, we know that the value of K is 8.9. Is this clear? Ethan, Mohammed, is this clear?
Yes, sir.
So it's going to be H plus 1 squared and divided by the acid concentration, which is going to be 0.25 mole per dm cube. Now remember, sometimes the concentration of these two are not exactly the same. Over here, it is exactly the same, because one FeCl3 is going to produce one Fe3 plus aqueous, and it's going to produce one Fe3 plus complex ion when it dissolves or mixes in water. So that's how a complex ion is going to be formed. Can you figure out what H plus 1 is, and can you do the negative log of that and find the pH?
So it's 1.82.
The pH?
Yes, sir.
All you have to do is you have to figure out the concentration of the negative log of H plus 1 ion, and that's your pH. That's 1.82, right? So it's coming out to be 1.82. The next part is, remember that how a complex is formed whenever you mix a metal ion and it dissociates and mixes with the solvent, and the solvent has lone pairs, like water has lone pairs. So all these water molecules, they're going to come and they're going to form coordinate dative bonds. That's going to be your coordinate number. So this one would be an octahedral complex. When 6 water molecules bond with it, that's an octahedral shape. And the overall charge would be 3 plus because, I mean, this is the complex that's going to be formed because water is neutral. So it's not going to add any charge. So it's going to be Fe3 plus 6 water neutral molecules. So it's going to be Fe3 plus. As the next one is the table shows numerical values of the stability constant for the following equilibrium, where 1m can be one of the metal ions listed and L one of the ligands, which replaces one water molecule. So what he's saying is M is the metal and L is the ligand. And remember, he's talking about octahedral complexes. So initially you have water molecules around it, 6 of them. So I'm going to draw. These are my X and Y axis. So I've got 6 water molecules that are surrounding. I mean, that's the original thing. So I've got 6 water molecules that are surrounding the M, the metal ion. And the metal ion has various charges. It's 3 plus, Fe is 3 plus. You got another 3 plus, you got Hg, which is mercury, which is 2 plus. So anyways, so this is, I mean, water is neutral. So what is happening is that one of the ligand comes in, only one of them, not more than one. Only one of them is coming in, and that one ligand is going to displace one of the water molecules. For example, this would be replaced by L minus 1. Okay, is this clear? Ethan, Mohammed, is this clear? Abdullah, is this clear?
Yes, sir.
So, I mean, these F minus 1, all of them have lone pairs, like Cl has lone pairs, Cl minus 1 has lone pairs. Not really sure. I think N over here has lone pairs. So SCN minus 1, it's going to have lone pairs. But anyways, what is the stability constant? Stability constant is the equilibrium constant of a ligand exchange reaction. This is the ligand exchange that's happening. So you've got a ligand exchange. Like if you add some other ligand, your ligands are going to get replaced. This is what happens when you have copper sulfate aqueous. It will be surrounded by water molecules. You add ammonia to it, you get a deep blue solution. Why do you get a deep blue solution? Because the water molecules get replaced by ammonia molecules. So anyways, what is meant by the term stability constant? So it's the equilibrium constant. I would have to actually check for the definition of this. So it's the general word term is that it's the equilibrium constant of a ligand exchange reaction when it is at equilibrium. So let me just quickly check this one because I've never actually seen them asking. I've actually never attempted 4-3 papers. Just a second. Is it not this one? So that was the last question. So it's the equilibrium constant for the formation of a complex ion from its constituent ions or molecules. So I said it was the equilibrium constant for a ligand exchange reaction. So for the formation of a complex ion, that would pretty much kind of be the same thing. But let's go with what they are stating. Because a complex ion is getting formed. So it's the equilibrium constant for the formation of a complex ion. I was just being a little bit more specific. For the formation of a complex ion. Okay, that's it. Then use the data in the table to predict the formula of the complex formed in the greatest amount. A solution containing equal concentrations of F minus 1 and SCN minus 1 ion is added to Fe3 plus. Now the thing is, remember it's the equilibrium constant of this ligand exchange reaction. Equilibrium constant is product concentration over reactant concentration. When does the equilibrium constant have a large value? It has a large value when you've got more products, right? So he's saying that he has taken Fe3 plus So there's an Fe3 plus complex. And he's adding both F minus 1 and Cn minus 1. So with F minus 1 and Cn minus 1, with F minus 1, the equilibrium constant is has a much bigger value compared to SCN minus 1. So we're comparing Fe3 plus reaction, its equilibrium, its ligand exchange reaction with F minus 1 and with SCN minus 1. So which one is more likely to be formed? Like which one is going to give you more products, the first one or the second one?
The first one.
Okay, Mohammed Ethan, is this clear?
Yes, sir.
It's going to be the first one. So he's saying use the data to predict the formula of the complex formed in the greatest amount. It's going to be the first one. So it's going to be Fe3 plus, and there would be I mean you can just substitute L over here. There would be 5 water molecules, and there's going to be 1 F minus 1, and the whole complex ion is going to have what charge? It's going to be 3 plus neutral minus 1, so it's going to be 2 plus. So the total charge is going to be 2 plus. You don't write the individual charges, so get rid of the individual charges. So it's just going to be Fe with 5 water molecules and 1 F. अच्छा उसके बाद a solution containing equal concentration of both Fe3 plus and Hg2 plus is added to Cl minus 1. So now he's talking about Cl minus 1. These two. Hg2 plus. So which one has the larger, which one has a larger?
HG.
It's going to be Hg. So it's going to be, just substitute this over here, Hg2 plus, 5 water molecules, and there's going to be 1 Cl minus 1. So it's going to be Hg2 plus and 5 water molecules and 1 Cl minus 1, and the whole thing will have a charge of, I think, 1 plus. Okay, that's going to be the charge. Remove the individual charges. So I'm just going to confirm whether this all is correct or not. Okay, so it's given over here that both of these are correct. So just remember that when you add an ion into a solution that contains ligands, the ligands get attached to it, and they could get attached in any number of formations. Like when there are 6 of them getting attached, that's an octahedral complex. You should know the shapes of the molecule. There could be 4 of them attached as well. That would result in a tetrahedral complex. So there could be all sorts of shapes of complexes, depending on how many complexes are, how many ligands are actually getting attached to it. There could be 2 of them getting attached only. That would result in a linear complex, but over here it was 6 of them, so that's an octahedral complex. And remember that ligands can be exchanged. You add water, water will surround it. You add ammonia, ammonia will surround it. You add HCl, it's got Cl minus 1, then Cl minus 1 ions will start surrounding it. The K stability represents how likely that's going to happen. How much product would be possible. If the value is bigger, you're going to get more products. If the value is lesser, you're not going to get a lot of products. TK, is this clear?
Yes, sir.
I said next one is you're being asked to write the K stability value for this thing, the complex. So you just have to write products over reactants. So these are your products, and these over here are your reactants. So it's going to be product concentration. It's going to be Fe. ED2. That's just a short name for, I think, abbreviated to this thing. TK, I mean, they've already said that ED is basically, ED2 minus is this thing, ethane diode. And it's got Cl2 as well. So Cl2. And so it's concentration. Remember, put the charge C minus inside. Square brackets represent concentration. You're not going to write water. Remember, whenever you write equilibrium constants, you never write water, especially if the solution is aqueous. All of them are aqueous, which means that water is in excess. And whenever something is in large excess, its concentration becomes constant. So you don't write water in the expression. TK, Ethan, Mohammed, is this clear? And then Abdullah, clear?
Yes, sir. Yeah.
And it's going to be ED2 minus concentration, and that one is going to be squared. TK, is this clear? Adam, is this clear? Ethan, is this clear? I mean, so can you hear me, Mohammed? I'm not really sure. Abdullah, can you hear me properly?
Yes, sir. I can hear you.
Adam? So now you're being asked to figure out the units for this. As you're being asked to figure out the units is concentration. That's I'm going to use x divided by concentration into concentration squared. So the x will get cancelled out, and it's going to be x to the power -2. So it's concentration to the power -2. That's going to be mole per dm cubed to the power -2. So it's going to be mole -2, and dm is going to be 6. Then you're being asked to draw complete the 3-dimensional diagram to show the 3 isomers of Ed2Cl2. So 3 isomers. Remember, this is Ed2 minus. I mean, this is the skeletal formula. So what's going to happen is that you're going to have 2 isomers. One of them would be the Cls would be on opposite sides, and the Ed, so that's where the Cl minus ones are with their lone pairs, and it's a bidentate ligand, which means that it's got 2 negative charges. There would be the same molecule forming 2 dative bonds, one of them from this side, the other one from this side, and the Cl minus 1 are on opposite sides. Okay. Is this clear? Can you guys hear me?
Yes, sir.
It is true, just answering someone, it's true for whenever something is in large excess. Remember, whenever something is in large excess, it has to be in large excess. So whenever something is aqueous, you just ignore water. You don't write water to it. That is exactly true. That is exactly what you do when you've got water. As anyways, what's the other one? The other complex is that the Cl minus 1 would be next to each other. So the Cl minus 1 ions could be right next to each other, and the Ed2 minus ligands could be next to each other as well. So that's the other isomer. But remember specifically this one, that when you have this one, it forms 2 mirror images. Whenever you have a bidentate ligand and there are 2 of them, and on 2 sides, let's say there are Cl minus 1 ions, it's going to form mirror images. There's going to be another version of the molecule which is going to be exactly mirrored. So all you have to remember for, I'll just revise, and here's your other one. So I'll just revise cis and trans complexes. One of them is, this is easy. Like if you have ligands, you could have, we can just have a quick look at cis and trans isomers in complexes. You just have to remember the simple ones. So maybe if I can, so you just have to remember the simple ones. For example, in octahedral complexes, you've got this thing. You can have 4 ligands of one type, and you can have 2 ligands of some other type. That would be, they could be opposite to each other. That would make an angle of 180 degrees. That's a trans complex. Or you could have 4 ligands, exactly the same arrangement, except that the 2 CNs might be next to each other. So that's going to be your cis version. So remember, there's going to be cis and trans versions in octahedral complexes, especially if you have 2 ligands of one type and 4 ligands of another type. That also kind of happens when you have 3 ligands of one type and 3 ligands of another type. So that can also happen in this one. I'll do the other example, which is, so where's the question? So I'll do another example. Let's say you have a metal line and you have an octahedral complex. Let's say this is your X and Y axis. So let's say you have 3 water molecules and 3 ammonia molecules. So the thing is that the 3 water molecules could be right next to each other. All 3 of them could be on one side. And all the 3 ammonia molecules could be on the other side. So that could also be, it's not called cis and trans, but that's also geometric isomerism. And because over here, if you look at all the water molecules, they're not making angles of 180 degrees. They're all making angles of 90 degrees to each other, because they're on all of them are on X, Y, and Z axis. There could be another version of this, which is that what I can do is I can switch the water molecule with an ammonia molecule. So the water molecule could be over here, and I can send the ammonia molecule to the other side. Now that's another version where the water molecules are 180 degrees apart, and the ammonia molecules are also 180 degrees to each other. So is this clear? Ethan Mohammed, is this clear that when you have an octahedral complex, it's either 2 ligands of one type and 4 ligands of another type, or 3 ligands of one type and 3 ligands of another type? That would result in the formation of geometric isomers. Is that clear?
Yes, sir.
Yes.
I said, then you have to remember that you can have geometric isomers in square planar molecules as well, which is, you have to remember a very specific anti-cancer drug. In a square planar molecule, like you can have a shape, there's cisplatin and transplatin. So a platinum ion is bonded to 2 Cl ions, and on 2 sides it's bonded to NH3 molecules. And there's another version of it. I mean, you can kind of guess what this other version is, that the 2 Cls could be on opposite sides to each other, and the 2 NH3s could be opposite to each other. So you have to remember this specific example of cis and transplatin. Is that clear? So is this clear? Yes or no?
Yes, sir.
So remember geometric isomers. Either octahedral complexes, where you have a 2-4 arrangement or a 3-3 arrangement. The CLs could be opposite to each other, or the CLs could be next to each other. You could have a 3-3 arrangement. The water molecules could be facing each other, opposite to each other, or they could also be next to each other. So the next one is, and also remember cisplatin and transplatin. The other thing that you should know of is, so this I think is, this is exactly showing the same thing. This is your cisplatin. So we're lucky we have these images now. So I think this is your cisplatin and transplatin. The CLs are next to each other. The CLs are exactly opposite to each other. This is the kind of molecule that we are actually doing. And we had an ED2 minus molecule, which was a bidentate ligand. I mean, it was a bigger molecule where you got a lone pair bonding from one side and you got a lone pair bonding from the other side, but it was the same molecule, but different parts of the same molecule. Even in this case, you're going to have 2 different versions. One of them is this one. The other one would be that the CLs are opposite to each other. So that would be your other version. Now I'm going to talk about optical isomers. Remember optical isomers in complexes. So let's just Google this. So for optical isomers, you got to just know these two. These 2 would be enough. Optical isomers are formed when you've got bidentate ligands. A bidentate ligand is this one. Like this is a rough example of how the molecule would look like. There would be a bidentate ligand attached over here, a bidentate ligand attached over here, and a bidentate ligand attached to these adjacent axes. And there's going to be a mirrored version for this. So that is when optical isomers are going to be formed. They would be mirror images of each other. No matter how you rotate this, this is never going to look like this. So I'll give you an example of a bidentate ligand. It's I mean, this is another example. So you could have another version where you could have two of them could be bidentate, and you could have Cls on the other side, or any complex over there. So, but at least two of them should be bidentate. So even then they can form mirror images of each other. But at least you need two bidentate ligands. So it's either three, or on the third side, you might have two Cls or any other ligand. Is this clear?
Yeah.
So they're asking you to draw. So now he's saying give the letters of the two isomers of which are geometric isomers of each other. So it's going to be C and A, or C with B. I mean, it's in both cases the Cls are next to each other. Over here the Cls are opposite to each other. So geometric isomers, and give the letters of the two isomers which show optical isomerism. These two are mirror images of each other. So it's going to be A, and it's going to be monodentate ligands definitely don't have. Don't have optical isomers. Just remember, it's very complicated. Like you can have a number of combinations. TK, I'm just answering someone. You can have a number of combinations. But you have to keep it simple. Remember, they're not going to go into a lot of detail when they talk about isomerism. The only thing you should know about is cisplatin, transplatin. Keep it simple. I mean, by just looking at it, you would know that it's going to have geometric isomers. The Cls could be opposite. The Cls could be next to each other. So don't go into a lot of detail, because there's a lot of combinations that are possible. But you don't have to go into a lot of detail. Even for optical isomerism, just stick to the simple ones. That's it. Two bidentate ligands, on two sides you got Cls, so it's going to form mirror images, or all three. Like in this case, all three are bidentate ligands. Even then it's going to form mirror images. So just keep things simple, because optical isomerism in complexes is pretty complicated, but they're not going to ask you very complicated stuff. So we're going to keep things fairly simple. As the next one is give the letter of the two isomers. We did that. Give the letter of the isomer which has no dipole moment. So it's going to be this one, because the dipoles will cancel out. Is that clear? Mohammed
Yeah.
Ethan, is this clear?
Yes, sir.
Because the Cls are opposite to each other, and the oxygens are opposite to each other as well. So all the dipoles are going to get cancelled out. So that's it. That was the last question. We'll move to the previous one, which should be, it's about. So let's do this. This is the mechanism of nitration. So you're saying the reaction also forms an isomer of 4-nitro methylbenzene as a byproduct. Draw the structure of this byproduct. This also reaction forms an isomer of this. So remember, a methyl group is what? It's a 2,4,6 directing group. I mean, what it does is that it pushes electron density, and the electron density increases on these carbon atoms. It increases on these carbon atoms, and all the other electrons, they get pushed. So the electron density is higher at position number 2 and 4 or 6. So he gave you a 4 isomer, the NO2 plus 1. The NO2 plus 1 electrophile is created. It's going to get attracted to the 4th position, or it might get attracted to the 2nd position. So the other byproduct is going to be this one. That what you're going to have is you're going to have CH3, and the NO2 is going to be at this position. So that's going to be, remember, you got two types of electrophilic substitution reactions of benzene. One is bromination or chlorination, where you need a catalyst, FeCl3, FeBr3. And the other one is nitration, where you need a temperature of 55 and concentrated nitric acid and sulfuric acid are used, which generates the NO2 plus electrophile, which attracts the electrons in the benzene electron cloud, bonds with it. And in the next step, the H is the one that actually ends up losing those electrons. TK, is this clear? Ethan, Mohammed, is this clear? Adam, is this clear? And you also need to know the reaction of how the nucleophile is created. It's going to be NO2 plus 1 that's going to be produced, and I think it's 2H2SO4. There's going to be 2HSO4 minus 1 ions, and not plus 1 ions, minus ions. And it's going to produce an H3O plus 1 ion. So the next thing is describe the structure and bonding of the 6-membered ring, and intermediate T differs from that in methyl benzene. So describe how the structure and bonding of the 6-membered ring. So it's a 3-mark question. So this one, remember what happens in benzene, the structure of benzene. The structure of benzene is that every carbon atom, so I'm going to draw the structure of benzene, every carbon atom is sp2 hybridized. What that means is that every carbon atom is just making 3 bonds. So remember, carbon has 4 electrons. So right now, only 3 of them are getting used up. So each carbon atom is making 3 bonds. And the 4th electron, let's draw it with this. So the 4th electron is initially not doing anything. So the 4th electron is unused. And the 4th electron ends up making a pi bond. So they all start overlapping, all of them. And there's this huge electron cloud that's covering benzene on top of it and below it. The electron cloud density is really less because it's very spread out. What happens when an NO2 plus 1, I'm talking about the intermediate here. What happens when an NO2 plus 1 electrophile, when it attacks it? What it does is that it sees the electrons, it immediately attracts those electrons. So what happens is this electron, which was busy forming these pi bonds, it's now no longer going to be available to form pi bonds. And this electron will get pulled towards the NO2 plus 1, and its positive charge would go away and it will bond with it. So is this clear? Is this clear? Mohammed, Ethan, is this clear?
Yeah.
Yes.
And so now the thing is, one of the carbon is now making 4 bonds. So that means it is now sp3 hybridized, unlike all the other ones which are sp2 hybridized. So he's saying describe how the structure and bonding of the 6-membered ring differs from that in methyl benzene. The first thing is methyl benzene had a complete benzene ring. So all of them were sp2 hybridized. So methyl benzene, I have to check what the answer states, but let's describe the difference, because remember how it differs. So methyl benzene had 6 sp2 hybridized or hybridized carbon atoms. Whereas this intermediate that we are talking about above, that contains 5 sp2 hybridized carbon atom. One of them is now making 4 bonds. So that's sp3 hybridized carbon atom. So what else? That carbon is making single bonds. It's all of them are sigma bonds. So one of the carbon atoms is making, remember, a single bond is always a sigma bond, while the other ones are making 3 sigma and 1 pi bond. So that is something that they are going to talk about. So I'm just going to check the marking scheme for this, which states it's the previous question. Just a second. So this one, he's talked about The sp3 hybridized in T, there's one carbon atom that is sp3 hybridized. So we got point number 3 for that. We talked about the pi electron clouds. Remember the sigma and pi bonds. Did he give us marks for that? So he's saying methyl benzene has 2 more pi bonds, delocalized electrons. So he counted the pi bonds. He gave us marks for that. Maybe he's going to give us marks for counting the sigma bonds as well. I said that one carbon atom is making 4 sigma bonds, while 5 of the carbon atoms are making just 3 sigma bonds, and they're making 1 pi bond. So we'll probably going to get marks for that. He's just stated that in a different way. And then he's giving us the angles as well. We should have given the angles as well. We missed that part as well. The carbon is tetrahedral, this one. So that's 109.5 degrees. And because I was focusing on bonding, he also talked about the structure, the shape of the molecule. These carbon atoms are fan-shaped. They are 120 degrees. And what's the 4th point? More delocalized electron clouds. That's obvious because there's more pi bonding. This one, pi bond extend over only 5 carbon atoms. The 6th one wasn't making any pi bonds. So that's also fine. Is this clear?
Yes, sir.
So then you've got this reaction. So I just thought it was 3 marks, so I just didn't write enough. So maybe you should have gone into a lot of detail about everything that's happening to this intermediate. Now, benzocaine is used as a local anesthetic. It can be synthesized from, so this is a reaction given. Give the systematic name of W. What's W? It's, I said W is benzoic acid. And remember, NH2 becomes amino, so it's 4 amino. Benzoic acid. Remember, carboxylic acids, they always have a much higher precedence compared to the other ones. Now, the next thing is suggest reagents and conditions for step 1 to 5. So step 1 to 5, each one of them. Step 1 is NO2 turning into NH2. That is reduction. Remember, that's 10 plus concentrated HCl. I can open a chart for this. Just 1 second. For all the benzene reactions, just a second, not AS. But 1 second, what's so this chart. We've got this chart. NO2 turning into NH2. I can't really find where NO2 is turning into NH2, but this one. NO2 turning into NH2. That's 10 plus concentrated HCl. So that is what is required for NO2 turning into NH2. A nitrobenzene turning into phenylamine. So that is what is needed. Where's the paper? Step number 2 is that's the formation of an amide. To form amides, you need acyl chlorides. It's going to be CH3, C double bond O, and Cl. The Cl and the H are going to be knocked out and they're going to form an amide. So all you need is an acyl chloride for that. And then what happens next? The CH3 turns into a carboxylic acid. So the CH3 turns into a carboxylic acid. So how do you do that? The way you do that is, like, if I look at the chart, you oxidize it. So I don't know if there's oxidation given over here. Just a second. Where's arenes? Do we have arenes here somewhere? This one. You got a carbon chain next to benzene. If you oxidize it using KMNO4, acidified, and reflux, oxidation happens. Whatever the carbon chain is, it turns into a carboxylic acid. So remember that as well, that it turns into a carboxylic acid. So this one would be oxidation, KMNO4, acidified, and reflux. Then the next one is the amide breaks up. So remember, amides can be, like esters, the amides can be hydrolyzed by two things. So you just have to add dilute acid and you can reflux or heat. The amide will break up and it will turn into NH2. So that's what's going to happen. The next one is step number 5. What's step number 5? It's an ester formation. So you're adding an ethanol molecule. I mean, the carboxylic acid turns into an ester. So you're adding an alcohol to it, which is specifically ethanol that you're adding. So the carboxylic acid turns into an ethanol. All you need is you need a concentrated. And remember, it's carboxylic acid, so that's fine. You need concentrated H2SO4 for that. Okay, so that's how ester formation would happen. So is this clear? All 5 steps. Mohammed, is this clear? Ethan? Adam, is this clear?
Yes, sir.
I just suggest how the basicity of benzocaine would compare to that of ethylamine. Explain your answer. So I don't know what benzocaine was. This one. Benzocaine with what? Ethylamine. So remember ethylamine is this thing. So you're going to talk about which one is going to be more basic. Remember, alkyl amines are always more basic because they've got an electron donating alkyl chain. That's what you're going to write. That they've got an alkyl electron donating alkyl chain. So the electron density on the lone pairs would increase and there's going to be stronger attraction for H+1. Why would this benzocaine be a weaker acid? Because the lone pair are going to mix up with the benzene electron cloud. When it mixes with the benzene electron cloud, the lone pair charge density decreases. And when it decreases, it becomes there is no lone pair, so it's not going to attract H+1 that strongly. TK, is this clear?
Yes, sir.
So then the next part, remember, you're going to get this question very often. It's either going to be about acids or bases. For bases, just remember that this is a weak base whenever NH2 is attached to a benzene. With amides, it's not basic at all because when you have an amide, the lone pair completely gets delocalized or pulled towards the oxygen atom. So it's hardly basic. Now, a sample of benzocaine is shown, was analyzed by proton NMR, carbon-13 NMR. Remember, this is carbon-13 NMR, which is exactly the same as hydrogen NMR, except that there's not going to be any splitting. So predict the number of peaks that would be seen in the carbon-13 NMR. So remember, the peaks are dependent on the chemical environment. So how many different carbons do you have? So let's rub this off. So remember, this first carbon over here at the bottom, that's different from all the other ones. That's number 1. These 2 carbons have an identical environment. These 2, the ones that I'm circling. So that's peak number 2. These 2 carbons are identical and they're different from the others. So that's number 3. This carbon at the top, that is different from the others. So that's 4. This carbon is different from all the others. This carbon is different from all the others. This carbon is also different from all the others. So these 2 carbons are exactly the same. These 2 carbons are exactly the same as well. So that's 1, 2, 3, 4, 5, 6, and 7. So you're going to get 7 different peaks, 7 different environments. Is that clear?
Yes, sir.
So that's going to be 7. And then benzocaine was dissolved in CDCl3. And now this is the proton NMR. This is the H NMR. Remember, H NMR also depends on chemical environments, except that there's going to be splitting according to the N+1 rule, which is that if the neighboring carbon has N hydrogens, the peak will split into N+1 peaks. So suggest why CdCl3 and not CHCl3 is used as a solvent, because CHCl3 has protons in it, which will resonate. So you're going to get, if you use this as a solvent, you're going to get some additional peaks because of that. And you don't want that. You just want the molecules peak. You don't want the solvents peak to appear in the chart or in the diagram or in the graph. So I'll just see how he's worded that. This thing. CDCL3 will produce no signal and would be detected. So that's it. It's going to produce its own peaks. That's it. Then you've got use data in the spectrum to complete the table for the proton. NMR spectrum of benzocaine, the actual chemical shifts for the 4 absorptions have been added. So first one, remember this one, 3 peaks. So that means according to the n+1 rule, the neighbor has how many hydrogens? It's got 2 hydrogens. The n+1 rule. So it's going to be this one, CH3. I mean, this is going to be this one. Because the neighbor had 2 hydrogens. So which is why it split into 3 peaks. It's a triplet peak. It's a triplet peak because the neighbor had 2 hydrogens. Mohammed, Ethan, is this clear? Adam, is this clear?
Yes, sir.
So what about the next one? This CH2 over here. Its neighbor has 3 hydrogens. So it's going to be, I mean, this one would be a triplet. This one over here is going to be a quadruplet because the neighbor has 3 hydrogens. So it's going to be this one. So this is that one. So what about the other peaks? NH2, remember, NH2 and OH, they never split. So this is going to be this one. And then you've got these 4 hydrogen, there are 4 hydrogens over here. So the last one is going to belong to this. So you don't even have to look at the data booklet. All you can do is you can just write down the spreading pattern, which we just wrote over there, triplet, quadruplet. That's a singlet, and this one is a multiplet. The first one was a CH3. So the triplet peak was for CH3 at 1.2. So the group responsible is CH3 next to a carbon chain. And number of H atoms, that's 3. And the splitting pattern is a triplet. At 3.5, you had a quadruplet, and the group responsible was CH2 next to an O. So the group responsible was CH2, which had a carbon chain on one side and it had an oxygen on the other side. So it had 2 hydrogens, and that was a quadruplet peak. And at 5.5, you had a singlet, which belonged to NH2. 2 hydrogens. Remember, NH2 and OH are always going to be singlet because the lone pairs shield them. So there's no interference. There's no mutual interference, which is why the peaks don't split for NH2 as well as OH. Is that clear?
Yes, sir.
So finally, it's so explain the spreading pattern. So what you're just going to explain this, that at 1.2, the neighbor has 2 hydrogens, so it splits into 4 peaks. I don't think they would ask for details. Just adjacent carbon has 2 protons, so that's it. I mean, that's just 1 marks for that. And also remember, don't go into the details of why splitting happens. I mean, if you just want to be quick with it, all you have to know is that you'll have different chemical environments. These hydrogens are similar. These hydrogens are similar. These 4 hydrogens are kind of similar. The NH2 is similar. So there are 4 different chemical environments. There are going to be 4 different absorptions. And if the neighbor has N hydrogens, it's going to split into N+1 peaks. The OH peak never splits. The NH2 peak never splits. And the OH and NH2 peak, they disappear because their protons are they can lose and gain protons. The other ones, they can't ionize. But NH2 and OH, they do ionize, which is why the protons can be gained as well as lost. So when you add D2O, where's he adding D2O? When you add D2O, which is heavy water, those protons, they disappear. Instead of the ROH, because of the ionization that's happening, it might turn into RO -1D plus 1. So it's going to become ROD. Deuterium doesn't resonate. Remember that. So the peak would disappear. The NH2 peak is going to disappear. Is this clear? Yes or no? Is this clear?
Yes, sir.
And then he's saying, benzocaine, we did dye stuff recently. He's saying you're making dye stuff from it. So the first thing is you have to make it into a disonium ion. So the NH2 needs to be turned into N triple bond N plus 1. Leave the things over here as it is. For that, you need NaNO2 plus HCl. And that disonium ion is very unstable, so the temperature has to be less than 10 centigrade. We have, I mean, you can have this over here in the spider chart. You start off with NO2, and I mean, you start off at NO2. I mean, what did we have? Just 1 second. You start off at NO2. This is an incorrect diagram, actually. Maybe ignore this. Actually, we're going to ignore this chart. We have to remake that chart. Made a mistake. It's always NH2. And that NH2 gets converted to N triple bond N plus 1. And then what you have is that the N triple bond N plus 1 is very interested in the electrons in this activated benzene. Remember, you need an activated benzene. So what happens is this phenol and the N triple bond N goes and bonds with the benzene, and you got a CO2 and a CH2CH3 over here. So this thing, this disonium ion gets attracted to the benzene, and it has to be an activated benzene. So it goes and bonds with it. Is this clear?
Yes, sir.
And suggest the reagents used for step 1. That's it. We wrote that down, NaN2 plus HCl. And he's saying suggest structures for compound. We did draw them, TK. So we drew them. And that's how you're going to do this. Now, so now the next, this is the previous part. He's saying the functional group present in P. So that's name the functional groups. You got a nitrile, you got an alkene, you got a benzene. Remember, benzene is a functional group as well. Compound P can be polymerized. Draw a section of the polymer, drawing 2 repeat units. So, I mean, draw the whole thing. You got a double bond. You got a CN on top, a CN at the bottom. You got an H over here. And I'll just write a condensed form that's C6 and H4, I think. So it's C6, H is 4, and you got 1 Cl. And they're going to link up. So they're going to link up and they're going to bond to each other. So that's what's going to happen. Type of polymerization, that's addition polymerization. And the next thing is complete the following table to show the structure of the process formed and the type of organic reaction when P reacts with 4 reagents. With the 4 reagents, it's Br2, KMNO4, hot concentrate HCl, and H2. So first one, I mean, it's obvious Br2. Br2, the bromine is going to get added to the double bond. Remember, the bromine is not going to get added to the benzene because for that you need an activated benzene. You need a catalyst for that, which is FeBr3. So that's one. Hot concentrate KMNO4, it's going to get oxidized. The carbon chain will break off remember it's hot KMNO4. So the carbon chain will break off and this part would turn into a carboxylic acid. And what else do we have? It's excess hot concentrated MnO4. Similarly, the double bond will also break off over here. This part will turn into this part will turn into a carboxylic acid, and this part, so it's basically this part. Let me forget this. This one will turn into a ketone, and this one over here will turn into a carboxylic acid. And remember, whenever you have an alkyl arene, it turns into a carboxylic acid. So remember the rule that the double bond is going to break, and you're going to have three options. One is that both of them would be H, that's carbon dioxide and water. One of them is R, that's going to be carboxylic acid. If both of them are carbon chains, that's going to turn into a ketone. Okay, is that clear?
Yes, sir.
So I'm just going to share some charts in the group. TK, just a second. Specifically for A2. Make sure you revise these. Today, let's talk tomorrow then, TK. Okay, everyone.
Thank you, sir.
Take care.